Every day, computer systems sift through billions of records to find a single piece of information. At this massive volume, navigating data without a precise plan would make modern digital services too slow to be usable. To solve this, developers rely on a specific partnership. Every program is a combination of data structures to hold information and algorithms to process it. One of the most common structures is the array, a simple linear list. If a program needs to find one number inside that array, it uses a search algorithm to step through the list. The design of that search determines the outcome. It is the difference between a system that handles growth smoothly and one that buckles under the weight of its own records. The most intuitive approach is the linear search. This method, also called a sequential search, simply checks items one by one, starting from the very first box. It is easy to write and requires no special organization. Because it checks everything in a row, it works on messy, unsorted data. This shows the search moving through an array. The computer evaluates elements left to right until it hits a match. But in the worst-case scenario, if the target is the last item, or missing entirely, the computer must check every single box before stopping. In an array of 20,000 items, a linear search might require 20,000 separate operations. Computer science calls this ON, or linear time, because the work increases in direct proportion to the number of items. Linear scaling is a trap for large systems. As datasets grow into the billions, this one-to-one relationship causes processing times to explode, making a smarter methodology a requirement. To search faster, we have to change the state of the data. The array must be completely organized and sorted before the search even begins. With a sorted list, we use a binary search. Instead of starting at the edge, the algorithm jumps directly to the exact middle element. It asks, is the target higher or lower? If it's lower, the computer ignores the entire right half, discarding thousands of records instantly. The algorithm then finds the middle of the remaining section and asks the question again. It repeats this divide-and-conquer loop until only the target remains. This structural rule changes the nature of the work. Searching is no longer about manual counting. It is a process of rapid, exponential elimination. The efficiency is easiest to see in the numbers. An 11-item list takes 4 tries. Triple the volume to 32 items, it requires 5 tries. Scale to 250 items, it finishes in 8 operations. Doubling again to 512 items brings the total to 9. This reveals a mathematical pattern. Every time you double the size of the dataset, the computer only adds a single extra step of work. This pattern is known as logarithmic time, or O of log n. This O log n efficiency allows programs to handle massive growth without requiring an equal increase in processing time. This efficiency acts like a precision tool, cutting through a massive data problem until only the answer remains. Consider that 30,000 item problem again. A linear search might require 30,000 distinct checks to guarantee a result. But the math of the binary search tells a different story. Since 2 to the 15th power is over 32,000, the computer can find any item in that list in a maximum of just 15 tries. This logic is the foundation for more complex systems, including binary search trees, which are built entirely around these rules of rapid division. Comparing 30,000 checks to just 15 shows that structural logic can provide performance gains that raw hardware speed alone cannot achieve. Real-world processing efficiency comes from finding mathematical shortcuts through an endless universe of data.